Hello, students. Last class, we briefly analyzed the relationship between the reactive power of the power system and the system voltage, and knew that the system voltage needs to be regulated. So today we will learn about what are the voltage regulation measures of the power system. First of all, there are contrary control of voltage, natural control of voltage, and constant control of voltage in the power system. The so-called contrary control of voltage refers to a voltage regulation method when in the maximum load, increase the system voltage pilot node voltage to 105% times the standard voltage to compensate for the increasing voltage loss on the line. When in the minimum load, reduce the pilot node voltage to the standard voltage to prevent the receiving end voltage is too high. Natural control of voltage refers to the voltage regulation method that appropriately reduces the pilot node voltage at maximum load, but not lower than 102.5% of the rated voltage, and appropriately increases the pilot node voltage at minimum load, but not higher than 107.5% of the rated voltage. Constant control of voltage refers to the voltage regulation method, in which the voltage at the pivot point of the system voltage remains basically unchanged, no matter how the load changes. Generally maintain the pilot node voltage at 102% to 105% times the rated voltage. The automatic voltage control that we often refer to, AVC, is the use of contrary control of voltage. As we know from the previous lesson, once there is a shortage of reactive power in the system, it will have enormous impact on the system voltage. So several measures need to be taken. The main measures that should be taken when there is a shortage of reactive power are 1. Require all types of users to increase the power factor of the load to the value specified in the current regulations. 2. Exploit the reactive power potential of the system. For example, temporarily idle generators in the system can be converted to operate as condenser and mobilizing the user's synchronous motor for overexcitation operation. 3. Add the necessary reactive power compensation capacity according to the needs of reactive power balance and allocate the compensation capacity according to the principle of local balance of reactive power. Small capacity and decentralized reactive power compensation can be used as static capacitor, large capacity, and configured in the system pilot node of the reactive power compensation. Is appropriate to use synchronous condenser or static compensator. The so-called voltage pilot nodes are those nodes or boxes that can reflect and control the voltage level of the whole system. The reactive voltage control at the pilot node is crucial, and the following are generally selected as the pilot nodes according to the actual situation. 1. The high voltage bus of a large power plant. 2. The secondary bus of a hub substation. 3. The bus bar of a power plant with a large number of local loads. Power system voltage regulation equipment as shown in the table, mainly generators, condensers, shunt capacitors, shunt reactors, and load tap changers. Among them, generators and condensers are characterized by the fact that they can continuously regulate without constraints on the number of regulations and can quickly respond to the disturbance of reactive voltage in the system in time. They are the main source of reactive power in the system, which can establish and maintain the voltage level, ensure the balance of reactive power in the system, and reduce transmission loss. The characteristic of shunt capacitor and shunt reactor is that they belong to mechanical switching, with the constraint of the number of switching times, and the switching speed is slow. They are important reactive power compensation equipment that can maintain the voltage level and reduce transmission loss. The characteristic of load tap changer is similar to that of shunt capacitor and shunt reactor, which belongs to mechanical regulation with the constraint of regulating number of times and relatively slow regulation speed, which can improve reactive power voltage distribution and reduce the transmission loss. Well, let's take a look at the regulating measures of power system voltage. 1. Voltage regulation by varying the terminal voltage of the generator. Change the excitation current of the generator can regulate the generator end voltage. The general generator end voltage allows plus or minus 5% fluctuations, but for power plants that far from the center of the load, relying solely on the regulation of the generator's end voltage, cannot meet the requirements. 2. Voltage regulation by changing the transformation ratio of the transformer. This way is to realize voltage regulation by changing the distribution of reactive power in the system. In the case of insufficient reactive power in the system, cannot rely on this method to increase the system voltage. Usually, there are two ways to change the type of a transformer: on-load voltage regulation and no-load voltage regulation. 3. Voltage regulation by reactive power compensation devices, such as condenser capacitor bank, reactive power compensation devices. In a sense, are reactive power supply devices. Rely on reactive power compensation devices to regulate voltage. On the one hand, by maintaining the balance of the system's reactive power to maintain the system voltage level. On the other hand, relying on the reactive power compensation devices installed in the user side of the regulator can reduce the line's active power and voltage losses, thereby increasing the line voltage level at the end of the line to achieve the purpose of regulating the voltage. 4. Voltage regulation by changing the parameters of transmission lines. Voltage losses can be varied by changing the resistance and reactance of transmission lines. In general, the line resistance is certain mainly to reduce the line reactance to realize reduced line reactance, mainly by series capacitive compensation method. Because when the line load changes rapidly, capacitance can quickly respond to such changes, so as to achieve the purpose of regulating the voltage. Next, we explain each of these four measures in detail. 1. Voltage regulation by changing the generator terminal voltage. Changing the generator terminal voltage regulation is a costless investment and the most direct means of regulating voltage by changing the generator's excitation current to control the changes in reactive power so as to achieve the purpose of regulating the voltage. It is applicable to the power supply line. It's not long straight distribution grid for the multi-voltage level network with a long power supply line, and the large power supply range is not applicable because its voltage loss in different operation modes changes greatly. Changing the generator terminal voltage is generally not able to meet the requirements. The generator terminal voltage regulation of voltage regulation is generally country control of voltage in order to meet the quality requirements of the near terminal voltage. 2. Changing the transformation ratio to regulate the voltage. First of all, changing the transformation ratio regulator is to vary the transformer taps for voltage regulation. Secondly, the low voltage winding of the transformer does not set up taps for the double winding transformer only sets up taps on the high voltage winding side. For the 3-winding transformer, sets up taps on the high, medium, and medium voltage side. Ordinary transformer tap is relatively less, generally 3 or 5, only allows manual switching in the absence of voltage. On-load regulation transformer tap is more, up to 17, can be switched in the load operation applicable to the occasion of large voltage changes. On-load voltage regulation can realize contrary control of voltage, while unexcited voltage regulation cannot be. 3. Voltage regulation by changing line reactance parameters. Changing the line reactance parameters for voltage regulation is in the transmission line series access capacitor to compensate for the line reactance. Thereby, reducing the line voltage loss is able to achieve the purpose of voltage regulation. This voltage regulation method is generally used for 35 kV or 10 kV distribution lines with large and frequent load fluctuations and a low power factor, while for series capacitor compensation in high voltage or ultra-high voltage lines is to improve the transmitted power and static stability of the power system. 4. Changing reactive power distribution for voltage regulation. The generation of reactive power does not consume energy, but the transmission of reactive power along the grid causes the loss of reactive power and voltage in the grid. The method of changing the reactive power regulation is to compensate the reactive power load in parallel at the user's place to reduce the reactive power of grid transmission. When the reactive power compensation power supply is a parallel phase shifting capacitor, the capacitor can only send inductive reactive power to increase the voltage and cannot send capacitive reactive power to reduce the voltage. Therefore, at maximum load, the voltage is low, and all capacitor banks are put into use. At minimum load, the voltage is high, and all capacitor banks are withdrawn. When the reactive power compensation power supply is a synchronous condenser, during overexcitation, the condenser sends out inductive reactive power to increase voltage. During underexcitation, the condenser absorbs inductive reactive power to reduce voltage. Therefore, when in maximum load, the condenser is on overexcitation operation to increase voltage. When in minimum load, the condenser is on underexcitation operation to decrease voltage. This method of voltage regulation is more effective in high voltage grids, where reactance is much higher than resistance. In the low voltage grid with larger resistance is not applicable. Combining the above 4 types of voltage regulation, we can draw the following conclusions. 1. Generator voltage regulation doesn't need to increase the cost and is the main method of voltage regulation in the generator direct power supply system. However, in the multi-machine system, adjusting the excitation current will lead to the redistribution of reactive power between generator. At this time, the generator power regulation can only be used as an auxiliary method of voltage regulation. 2. When the reactive power supply of the system is sufficient, the voltage can be regulated by changing the transformer taps. The voltage regulating transformer can be connected in series with the circuit. For the radio network, the purpose is to regulate the voltage for the ring network. It can also change the power distribution. A series booster installed on the inter-system contact line also plays a role in isolation, so that the voltages at the two ends aren't affected by each other. 3. In case of insufficient reactive power, In the system, the voltage cannot be increased by changing the taps. The reason is that increasing the voltage by changing the taps will increase the reactive power required in the area, which will enlarge the reactive power deficit of the system and lead to the voltage level of the whole system to drop. In this case, the voltage regulation methods should use shunt compensation, shunt capacitors, condensers, static capacitors, etc., or series compensation that changes the line parameters, such as series capacitors. 4. For 10 kV and below voltage level grid, due to the load is dispersed and the capacity is not large, often according to the permissible voltage loss, to select the cross-sectional area to solve the problem of voltage quality. It is worth noticing that changes in the frequency and voltage of a power system affect each other. When the system frequency F decreases, the reactive power output of a generator equipped with an automatic excitation regulator will rise due to the fall in F, preventing the voltage from falling when the system frequency rises due to the role of the generator's automatic excitation regulator, which prevents the voltage from rising. So the generator's reactive power output eventually decreases. Due to the rise in frequency instead, the change in voltage also affects the system active load. When the voltage rises, the active load increases, causing the frequency to fall. When the voltage falls, the active load falls, causing the frequency to rise. Okay, class, do you learn all the above?